Welcome all to this 9th lecture of Principles of Statistics. In the last lecture, we proved the asymptotic normality of MLE, and this result really, well, it partly justifies the widespread use of MLEs, because of course, they enjoy all these very nice properties that we've been talking about. And then, on top of that, this is like an automatic way of building estimators, which is not actually conceptually very hard, right? So all of this justifies this widespread use of MLEs as frequentist estimators. Now, because the asymptotic normality of MLE gives us precisely a distribution, or at least an asymptotic distribution for this estimator, or some sort of centered and rescaled version of it, then it will allow us to not only estimate the parameter of interest, but also, construct other inferential procedures like confidence regions and hypothesis testing. So we'll do that today. We'll start with the confidence regions, and then in the next lecture we'll consider hypothesis tests. But before doing this, let me introduce an intermediate, well, not intermediate, but let me introduce a just a bit more advanced concept, which is what is called a plug-in MLE. And this is this is an idea, a general idea, for when, rather than wanting to estimate the parameter that is indexing the distribution, or the PMF or PDF, what we want to estimate is a function of that, right? And so that's a very typical case in practice, that we want to estimate a function of the underlying parameter. And so then the question is, how do you do this? Can you exploit the MLE for the parameter of interest to somehow say something about this function of a parameter? And so we'll answer this in the positive fashion. And again, it's not only about constructing an estimator, but trying to prove some sort of distributional properties of it. And so we will now introduce this through the delta method. And because of these distributional properties, we'll be able to unify, both the MLE and the plug-in MLE to construct confidence regions and hypothesis tests. So let's start then with this additional concept. So this is section 5. And this is, as I was describing, the plugin, so-called plugin MLE. And then the other thing I was talking about is what is called the delta method. Okay, also called von Mises method. Right. Okay. So let's consider then a statistical model as usual. So in a statistical model, so again, we have general, we have finite dimensional parameter space. So consider inference for a functional, right? And this we're going to call capital Phi. Capital Phi is going to go from the parameter space to some RQ now, with Q being greater or equal to 1, greater than or equal to 1, and then this capital theta. I remind you that is contained in RP, P greater than or equal to 1. Yeah. Okay. So we could give an example, right, of this case, and this is a very simple example, a very toy sort of case, which is, when we're not interested in the whole parameter, but rather just part of it, right? So imagine that, or suppose that we can express this capital theta as the product space, between 2 parameter spaces, capital theta 1 and capital theta 2. And so therefore, a parameter can be written, or the parameter can be written as this vector of vectors, if you like. And what, as I was saying, what we're interested in is, just part of the theta. So let's say, okay, that's not very clean. So, and this capital phi theta is going to be theta 1, say. Okay. So we can find an estimator, in this case the MLE, maybe an MLE, via what is called the profile likelihood. Okay, what is this? Well, it's a very simple idea. It just means, optimize over, first of all, let's define this profile likelihood. This is for the theta 1, this is a function of the theta 1, and this is going to be the soup over, this theta 2's of the original likelihood of these guys. Okay, and we can define the MLE as the arg max, okay, over the theta 1, of course. So it's exactly what you would expect, right? But we've defined this profile likelihood. Okay. So this is just a very simple example, and you'll see more about this in the example sheet. So let me just state result that you'll have to show. By the way, I've uploaded. So I uploaded the third example sheet yesterday. Second example sheet yesterday. So let's imagine that this phi is injective. Okay, so generally it's not necessarily what we're interested in, but what about, in the case in which this guy is injective? Well, then an MLE of the model where this phi is given by the image of the theta, where the theta is in the parameter space. So then this is given by this here. Okay, so this is exactly what is called the plugin. Well, you don't need the injectivity to talk about the plugin MLE, but this is the idea of a plugin MLE. So it's literally just plugging the MLE to the function that you're interested in, or the functional that you're interested in. Okay, so that's a very simple idea. And so the question is, does this make sense? And so at least we see now that if we have injectivity, then it makes sense, at least in the sense that this corresponds to the maximizer of the sort of the resulting likelihood after this reparameterization. Yeah. Okay. So this is in some sense inherited, the fact that it is the maximum likelihood estimator. But there is more that we can inherit, and this is what's key about the plugin MLE. So why it's powerful, it's a powerful idea. So when this guy is differentiable, we have that the inferential procedures for procedures of the MLE are, inherited by this plugin MLE. Yeah. Okay, and this is what is called the delta. Well, the specific result is the delta method, or also called, as I said earlier, von Mises method. Okay, so what does it say? Well, let's begin. So theorem 5. So we have our functional of interest. And so I'm going to state this for one dimension, yeah? Okay, so for one dimension, so let this guy be differentiable. Okay, and this has to happen at some theta, or maybe some theta naught, if you like. Yeah, okay, so we can just write theta, and let theta n hat, okay, so I didn't write the MLE, so be random variables in this space, such that we have, some asymptotic and distributional result. So we have that, this is an estimator. So this converges in distribution to some z for some random variable z, okay? Of course, this has to be in RP. Yeah, okay. So then we get the following. We get that the square root of the image, of the plugin MLE, not MLE, sorry, the plugin estimator. So this is more general than just the MLE. Excuse me. We can also say something about its limiting distribution, and we can even, specify what it is. Yeah. Okay. Just this in here. Okay, so if you look at it for a second, and you sort of remember how we proved theorem 4, then really you should, this limit on the right-hand side should be familiar to you, or at least not surprising, yeah? Because what we really see here is that we're using some sort of Taylor theorem, yeah? Or Taylor expansion, yeah? So that's really just the idea. So let's just prove this. So I guess maybe let's try it. So by the differentiability of this capital phi, we can write that the left-hand side equals, if we expand this around this capital phi at theta, then this should be just the derivative directly. And maybe let's take, yeah, okay, so this is just the derivative. And if you like, with the square root of n, just thinking, okay, so square root of n, and then the gradient of this capital phi at, the value theta. and then we transpose and we multiply by this guy minus this guy, and then we have some remainder term, and that is given by this with the small o of this quantity. Yeah. Okay. I mean, by the way, so I did state this for one dimension, so that double, those double vertical lines are really just the absolute value, if you like. Ooh. Okay. So we have this, and so it's really clear that this is deterministic, right? And this, when you put it together with that, will converge to this z, and so then just simply by Slutsky's lemma, if you like, then we get that the first term converges to what we wanted. Yeah. So maybe let's call these I plus first term plus second term. So by what I was just saying, this will converge to in distribution to this guy. So we need to show now that the second term is negligible. Yeah. Okay. So to show that, let me then just use again the convergence of these guys. And so what is this? This is converging in distribution to some z. And now remember what this means, or at least what this implies. So remember, the convergence in distribution doesn't give us convergence in probability, but it does give us boundedness in probability. Okay, so then we know that the square root of this theta n minus theta is, as I'm saying, PR of 1. Okay, and I guess even more so, you could say that, and the same happens to this. Okay, there's no difference. It's the absolute value, and if you like, you can say that. So the term that we're considering, which is small o square root of n of theta n hat minus theta, this is going to be small o and the PR of 1. Okay, and this is by so maybe before, let me just reason this. This is by the continuous mapping theorem. So this follows, yeah. Okay, and then we've shown basically the result, right? Okay. Okay, so let me make a couple of remarks. So the first one is that is something I was saying in words, and is that this guy is not is any such estimator. Okay, so one as in the statement. So in particular, not necessarily the MLE or an MLE. Okay. And in fact, more can be said, and is that the square root of n can be replaced by a different rate. Okay. Rn. Okay, so that looks a lot like square root of n, but that's Rn. Yeah. So what do I mean by this? Well, I mean that it could be that, you know, this estimator, this theta n hat, converges to theta not at this square root of n rate, but rather, you know, at something slower, like fourth, you know, the fourth root of n, and then, you know, that converges to the z. So for different rates, rather than square root of n, you get exactly the same result. Yeah. So of course, you know, if this changes, then this changes, but that's obvious, and the proof is of course just literally line by line, just the same. Yeah. Okay, and I guess. So that's what it is, and then as I was saying, so one can state this for you know, general dimensions. So there also exists so there exists precisely a version for this Q greater than 1, okay, case. And then the third remark is that, yeah, okay, so the third remark is that the plugin, so this plugin MLE is actually asymptotically efficient, okay? So this you may have realized already. And why am I saying this? Well, because we've actually seen this bound, or the bound that we need here, in the past. I'll state it now. So it's asymptotically efficient for estimating the quantity of interest, which is the image of this theta through the capital pi, i.e. This, you know, remember what we said, so the lim as n goes to infinity of this n variance of the theta, no, of this guy. So this is going to be precisely just the quantity that we saw in the theorem, and sorry, yes, I mean, it's a constant, and then of course we get here that quantity. Okay, so we saw this bound here. So when I introduced when I spoke about the Cramer-Rao bound, lower bound, then right after that I spoke about a multivariate version of it, and that was giving us precisely this quantity. Yeah. Okay. So let's say, let's just state that somewhere. So recall that the latter, so the right hand side is the Cramer-Rao lower bound. Yeah? Okay, so right, so we have asymptotic normality of the MLE and also of the plugin MLE, right? So now we want to use these asymptotic distributional results to construct inferential procedures. So asymptotic inference. Okay, and this is with the MLE. Okay, and this is of course the MLE or the plugin MLE, but plugin MLE needs the MLE. So as I sort of said when introducing the lecture, we can unify you know, the MLE and plugin MLE by considering, yes, of course, what I mean to unify is the inferential procedures. So by considering, and we can do, you know, first of all, just write this, okay, and this would be, just write it, so this is in Q. So, if you want to talk about the MLE, well, the MLE is just a plug-in MLE for the identity function, right? So that's what I mean here. I just mean that you can unify the two estimators by simply writing this, and this is, yeah, okay, so I'm writing that just to express any of them, yeah? Okay, so satisfying just the same as in the theorem, which is that the square root of n of this quantity minus this other quantity is going to go to some z, which is dependent on this capital phi, and this is again for some z capital phi, or some random variable z capital phi. Okay, in, of course, R Q. Okay, so Q could be P if you take the identity. Okay, so then let's. So as I said, today we're going to cover confidence regions. So let's begin with some example that we may come across, and so we may be interested in just one or two different examples are we may be interested in one of the coordinates. So this guy, or j going from 1 to q, or confidence region for the whole of this guy. So it could be so maybe just explicitly say for whole capital phi. Yeah. Okay. So let's start with the first one with coordinates. So for the former, what can we say? We're gonna first of all note the following, and is that we can write it simply as the product of the unit vector with the jth component being 1 and the rest being 0. And so, yeah, so as I'm just saying, this would be this vector, so it has all zeros except for the jth element that has a 1. Okay, so very simply by the continuous mapping theorem, we get, of course, that square root of n of if you like, n j, so the jth entry of the capital phi n hat minus this converges in distribution to this ejtz of capital phi, right? That should be sort of clear to everyone. That's converges in distribution. Okay, and okay, so then let's build, a confidence region, which in this case is a confidence interval because we are in one dimension. So let's define the region that I want to consider. So I will write this as, let me just write it as a function of alpha, and this is going to be, the set of phi's, and this is lowercase phi in R, such that they are away from this estimator by no more than the following quantity. And so this is going to depend now on this capital phi, but also on alpha, and then we're going to get this square root then, yeah? Okay. So, yeah, so then this guy, what we can say, let me, of course, define that zj we have in there, so where the probability of, so there's going to be now some zj here being less or equal than just 1 second. Yeah, okay, fine. I'm happy with this. So this being less or equal than this guy, which is non-random. So this guy on the right-hand side is non-random, while the guy on the left-hand side, so this guy, right? So it's just some, yeah. So it's just some random variable, which is the one we're considering above. Remove, just erase this. Okay. And assume, let us for simplicity, assume that this zj capital phi is a continuous random variable. Okay. Then we have that the C and J is going to satisfies what we want, which is that the probability of the true parameter, which is the jth entry of this capital phi, is, you know, if we look at the probability of it being in this set, then this is very simply just the probability of this just that this is here, and this is absolute value, right? That this being less or equal than this zj, non-random. So this, it should be clear to everyone that this converges to the probability of, you know, this zj being less or equal than this quantity. Okay, and that is, you know, that should be clear to everyone by convergence in distribution. Well, rather than being this guy, I guess it's just without the denominator. So then let's just write this. Okay. So convergence in distribution together with the assumption, this simple assumption of it being a continuous random variable, so that, you know, because I remind you that convergence in distribution is this convergence of these you know, these probabilities, but it has to happen just in the continuity points. Yeah. So not in every single point. Yeah? So if we have a continuity point everywhere, so all of them are, then this is just for. Yeah. Okay. So now let's look at the case in which we have the whole parameters for the whole capital phi. We can use what is called Bonferroni's correction. Okay, so what do we take? We take Cn for the whole parameter to be the product, and this is the product from J 1 to Q of this Cnj's at each alpha, but the correction comes precisely from, you know, dividing this alpha. Okay. Okay, and I state, and you can check this easily. I think it may be in the example sheets of the of statistical modeling. So this has coverage. So maybe because there is a new lecturer this year, and he may have changed the sheets, but otherwise, if he hasn't, then it should be there. So at least 1 minus alpha. Okay. 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 So maybe let's make one last observation, and is that, to construct, you may have realized this already, that to construct these confidence sets, so the Cn, depends directly on the Cnj's, and the Cnj's, on the right-hand side, we have this Zj that is going to depend on the capital pi, right? And the capital pi is actually the quantity of interest, yeah? So that is unknown, yeah? So then really we need to do something about it, because we cannot use something that we don't know about, yeah? Okay, so just taking this, note that this Zj, of course, depends on unknown okay. And so generally, we can swap this capital Phi by precisely what you're expecting. Yeah? So the estimator, yeah, the plug-in estimator. Yeah. Okay. To obtain the plug-in maybe let's say to use, yeah, rather than obtain, to use Zj, and then this guy, and this guy. Okay, so that's just, sort of continuing on the idea of plugging in the estimator into the function that we're interested in. Yeah. Okay, so now, so we've said a few things about this Zj's, but this Zj is a general random variable, and so when the distribution is known, we can be more specific about what we can say. Yeah. So when this Z is known, more can be said. Yeah. Okay, so let's maybe consider, an example, because we're going to take, let's see, so let me begin with these examples in which, as I was saying, we're interested actually in the parameter indexing the family, and then, the case in which we're looking at the MLE. Yeah. Okay. So then, in this case, what do we need to work out? Well, we need to work out the Zj's. So I'm, looking at the coordinates again. So this guy here, what is it going to be? Well, so this Zj is going to be okay. So I may have not defined. Yes. Okay. No. This is fine. Yes. So this Zj is, as we were saying, is this. Let's write it here. So this is just the jth coordinate actually of the Z, and if we look at, okay, so maybe check this yourselves. If you're looking at the MLE, then the Z is going to be a normal distribution. And so when you look at the jth component, then this is going to be just simply the Fisher information matrix to the -1. And then we look at the jth entry, okay? And the square root if we then just directly take the usual z alpha, which is just a quantity that satisfies this, where this capital Z is a normal distribution. Yeah. And we can estimate, again, so this guy now depends on something that is unknown, so we can theta as follows, yeah? Or maybe let's say, so by these guys, which I'm going to define in a second. So maybe let's write n theta n hat, which is of course the MLE, and also by another quantity that I'll define in a sec. So let me define this. So definition 5. So we have a P times P matrix. Okay, so the matrix given by this 1 over n, and then the sum over the data points of this log of xi theta, and then we multiply this by the same guy but transposed. Okay, yeah. So this guy is what is called the observed Fisher information. And we also define, and we define too, this Jn, okay, Jn. Theta being what you're probably sort of anticipating already, which is the negative of 1 over n of the sum from 1 to n of the second derivatives here. Okay, so let me introduce now a proposition 4, about these two guys, right? Because these two guys are sort of intuitive, right? That they should be, or at least, they make sense as estimators. So now we need to prove something about them. We need to say something about the properties, or the, that they have some desirable properties. So proposition 4. So under the assumptions of theorem 4, okay, so the asymptotic normality of the MLE, and also assuming that the expectation and the theta naught of the supremum of the space, of the parameter space of this. So we have a log here of the fx theta, then times the same quantity but transposed. Okay, so we wish this guy to be less than infinity. Okay, and so then we get that the in and the jn converge to, but this need to be hat, yeah? Because these are when we plug in the MLE, yeah? there. so we have this convergence improbability. Yeah, this is under the knot PR, and this converts, to the facial information matrix of this Theta. Yeah. Okay, so what's the idea to prove this? Well, it's something we've sort of seen. So one proceeds literally as in theorem 4, when we showed when we considered the AN, yeah? So the AN was converted into this I theta mat. Yeah? Okay, so this is in theorem 4. Yeah. Yeah. Okay, so this is just the idea. Okay, so let's maybe just make a last remark, because this is sort of pertaining the one-dimensional case, and so of course we can construct, as we were saying, we can construct the a confidence region for the whole parameter through this Bonferroni correction. However, this Bonferroni correction is actually not really good in general, yeah, as a confidence region, and this is because it's too large. Okay, so you can have different confidence regions with the same sort of coverage level, so they have the same probability of containing the true parameter, but it may be that they have very different volumes, yeah? And so of course what you want is to have the one that has smallest volume, and this is because if I guess maybe a reason that is quite intuitive to say that you want this minimal volume is that if you construct a hypothesis test from that, as saying, does this estimator belong to this set or not, or this value to this set or not, then if you look at the type 2 error, so the error that you make when you are considering an alternative, okay, then of course, if you have a very small region, then when the parameter of interest is not, so imagine the regions as being centered around a parameter that you think may be the right one, so that corresponds to the null hypothesis. If it is a different one, then you wish this guy to be as small as possible, so that as soon as you're a bit different, you're a bit off from it, then you come out of it, and then you reduce the test to the type 2 error. Yeah, because if it were very large, then even if you move a bit, then you actually will fall into it more than if it were smaller. Yeah. Okay. So for the whole parameter, for the whole well, in this case, I guess, yeah. So the parameter, as I'm saying, Cn is typically too large. Yeah? Well, not too, but large. Yeah? Yes, large. So, is there a better alternative? Yes. So usually a better, and by better I mean no worse coverage, comma, and smaller volume, size. So that the better confidence region is obtained through what is called, via the so-called walled device. Well, walled device, or walled statistic, I guess would be. Okay, so the world statistic. So what is this? Well, that's just following guy. So we have our, so maybe I'll introduce it and tell you about it intuitively why this is the right thing. So you could be taken here, so maybe it's for instance, so that it's clear with the MLE. It's theta, and then we're going to take now IN hat. You could also take, or say N hat, okay. And then you multiply this by the MLE. And by the way, this needs a transpose. Okay, so to build inferential procedures, we need to know, the asymptotic distribution of this guy, and this is given, this is actually simply given by, so in distribution, this is going to converge to a chi-squared distribution on p degrees of freedom. Okay. So let me pause here maybe and say why this is the case. Well, you should think of, so take the square root of one of these two guys, so take the square root of IN, say, hat. Rather than having IN hat, just imagine that is the Fisher information matrix. And so if you take the square root, if you take the Fisher information matrix as the product of the two square roots of itself, then you can separate it. And what you will get, remember the MLE will convert to a normal distribution with the inverse of the Fisher information matrix. So you will essentially get two standard normals, yeah? As the limit, and then this will convert therefore to chi-squared on p degrees of freedom. Yeah? Okay, so now, how do we construct the confidence region with this? So confidence ellipsoid is Cn. Okay, I'm gonna have to use one more line, I guess. So Cn is the I guess set of thetas such that this world statistic is less or equal than some psi alpha, where psi alpha satisfied, so just so that we don't need to use another page, let me just say that this is psi alpha, where this z, sorry, this should be 1 minus alpha, right? And the z is a chi-squared. P degrees of freedom. Okay. Okay. So I hope you enjoyed the lecture, and that I see you in the next one.